In this video, I will be discussing about Newton's second law of motion. We know that the Newton's first law of motion states that an object will preserve its state of motion unless acted upon by some external net force. Now, this Newton's first law of motion is very revolutionary because an object that is at rest will remain at rest unless acted upon by some external net force. Now remember that the external net force applied to the object must be an unbalanced net force, because if this is a balanced net force, it will not change the state of motion of the object. So when the object is at rest, it will remain at rest. And if the object which is in motion will remain in motion unless acted upon by some external unbalanced net force. But here, our focus is the Newton's second law. And the second law of motion by Newton states that the change of momentum of an object is directly proportional to the unbalanced force in the direction of the force. And we notice that this second law is just a continuation of the first law, because in the first law, the state of the object will remain the same unless acted upon by an unbalanced external net force. So, what if there is a net force acting towards the object? Then, therefore, we say that there is an acceleration that happens in that case. So, acceleration depends on the net force there. And to illustrate this one, suppose you have a globe at home and you want to spin this globe, which is in its stand. What will you do? You need to spin this globe here. And if you spin it with more force, there will be more acceleration that takes place. But when there is a lesser force to spin the globe, then there will be a lesser acceleration. In other words, acceleration depends on the net force applied to the object, which implies that the more force, the more acceleration will happen. And the lesser the force, the lesser also the acceleration. So we say that acceleration depends on the net force. Thus, mathematically we say that acceleration is directly proportional to the force applied to the object. Because if you apply more force, there will be more acceleration. And if you apply lesser force, there will be a lesser acceleration. However, acceleration depends also on the mass of the object. Now take note, we learned from physics that mass is different from weight. Because you know, mass is the amount of matter present in the object. So if you have a stone, a big stone on Earth, and you take the weight of the stone on Earth and carry the stone to another planet, say Saturn, the weight of that same stone will be different. Because you know, different planets have different gravitational pull. So therefore, weights vary from planet to planet. But the mass remains the same. Because this is the amount of matter present in the object. Now here, let us discover the relationship between acceleration and mass by illustrating this one by two stones. One is a small stone and the other one is a bigger stone. So this is the bigger stone here. But I will apply the same amount of force here. So force is applied to the smaller stone, the same force here. So what do you think will incur a greater acceleration? Is it the smaller stone or is it the bigger stone? Of course, common sense would tell you that applying the same force to this smaller stone and bigger stone, more acceleration happens in the smaller stone. So therefore, we conclude that the smaller the mass, the greater is the acceleration. And the bigger is the mass, the smaller is the acceleration. In other words, acceleration is inversely proportional to its mass, because when the object is having a smaller mass, it will accelerate more than the object that has a greater mass, given that the same force is applied to these two objects. So, equivalently speaking, the more is the acceleration, the lesser is the mass. And a lesser acceleration took place because the object has a greater mass, given that the net force applied to the two objects are the same. So, mathematically, we write in symbols that acceleration is directly proportional to the force, this one, and inversely proportional to its mass. And this is the Newton's second law of motion, that acceleration is equal to the force over mass. So if you do simple arithmetic, we say that the force is equal to the product of its mass and acceleration. Now, take note that the mass is the weight over the acceleration due to gravity times dv dt, because acceleration is the change in the velocity with respect to time in mathematics. So this is the amount of the net force applied. Now take note that the units of measurement for this net force is kilogram here, which is the unit of mass, and the unit of acceleration is meters per second squared. In other words, if you have 1 kilogram and 1 meter per second squared, that is equivalent to 1 Newton here. Thus, we can say that 1 Newton is defined to be the amount of force required to give 1 kilogram mass an acceleration of 1 meter per second squared. So, if you have an object whose mass is 10 kilograms and you want an acceleration of 5 meters per second squared, then the amount of the net force required is equal to 10 kilograms times 5 meters per second squared. And if you multiply this one, this is 50 kilogram meter per second squared. In other words, you need an amount of 50 Newton as the net force applied to an object whose mass is 10 kilograms to have an acceleration of 5 meters per second squared. Now let's have our first example here. A body weighing 445 newtons is drawn along a rough surface. The force applied in the direction of motion is 135 newtons, while the frictional force is 90 newtons. If there is an air resistance whose magnitude in newtons, which is equal to twice the velocity at any instant, determine the velocity and the displacement at any time t, assuming that the body is starting from rest. So to solve this problem, allow me to draw an illustration showing the situation in the problem. So suppose this is the object here. Let's represent this one just a rectangle here. And of course, this is the rough surface. And this object is weighing, so it has a weight of 445 newtons. So of course, at the start, so time 0, our displacement is also 0, meaning the object is not moving here at the start. So the velocity is also 0. But there is an amount of force applied to this object. So the force applied is equal to 135 newtons. But the surface is giving a frictional force which is against the force applied, because this is a frictional force of 90 newtons here. Also, it is given in the problem that it has an air resistance that is equal to twice the velocity of the object at any instant there. So this air resistance must be also in Newton here. And because the force here is greater than the frictional force, and of course greater than the air resistance, the movement of the object is going to the right also here. So it will incur an acceleration which is in meters per second squared. And of course it will give you a displacement, say up to here, after some time t. So this is our S here. So first, let us model the net force applied. And the net force can be calculated by its own mass times the acceleration that took place, which is the change in the velocity with respect to time. So the net force will be the force applied, which is 135, minus the frictional force, minus the air resistance, which is twice of its velocity. And this is equal to the weight, which is equal to 445 divided by the acceleration due to gravity. Because you know, mass is not the same as weight. So to compute the mass, we need to divide the weight by the acceleration due to gravity. And the change of the velocity with respect to time is our acceleration here. So simplifying this one, we have 45 minus 2v, which is equal to 445 divided by 9.8 meters per second squared, because 9.8 is our acceleration here due to gravity. So dividing these numbers here, we have 45 minus 2v, which is equal to 45.4 dv dt. So multiplying both sides of the equation by dt, we have dt, which is equal to 45.4 over 45 minus 2v. If you divide also both sides of the equation by this 45 minus 2v. And of course, do not forget that we have a dv here. Then you notice that this is a differential equation wherein the variables are separated. So you can take the integral of both sides here. So the integral of dt, which is equal to the integral of 45.4 over 45 minus 2v dv. And you can factor the constant outside the integral symbol, which is 45.4 here times the integral of dv over 45 minus 2v. But you notice that the differential of 45 is 0 and the differential of negative 2v is negative 2 dv, which we don't have in the numerator. So we need to supply negative 2 dv there, and to have a neutralizing factor because of that negative 2, we need to multiply by negative 1/2 also outside the integral symbol, so that negative 1/2 times negative 2, the product is positive 1, as if we have done nothing to the original integral. So we have t as the integral of dt, and 45.4 multiplied by negative 1/2, we have negative 22.7 times the natural log of this denominator of 45 minus 2v, because that's the integral of this du over u. So if this is our u, the integral is the natural log of our u plus the constant of integration c sub 1. But we can solve for this constant of integration if we use a boundary condition from the problem. And the boundary condition is the condition at the start. So this is the initial condition here. So when our time is 0, meaning at the start, the velocity is 0 because the object is not yet moving. So then our t, which is 0, is equal to negative 22.7 times the natural log of 45 minus twice of the velocity, which is 0, plus the constant of integration c sub 1. So 0 is equal to negative 22.7 times the natural log of 45 here. So our constant of integration is equal to 22.7 times the natural log of 45. Thus, our equation, which is this one, becomes t, which is equal to negative 22.7 times the natural log of 45 minus 2v plus the constant of integration, which is 22.7 times the natural log of 45. Now our goal here is to find the velocity, this one. So we need to isolate the term that contains the velocity at the right hand side of the equation. So we move this one to the left. So t minus 22.7 times the natural log of 45 is equal to negative 22.7 times the natural log of 45 minus 2v. And dividing both sides of the equation by negative 22.7, we have t minus 22.7 times the log of 45 divided by negative 22.7, which is equal to the natural log of 45 minus 2v. So dividing t by this negative 22.7, we have negative t over 22.7, and this negative 22.7 times the natural log of 45, when divided by this one, the result is the natural log of 45, and this is equal to the natural log of 45 minus 2v. Now you notice that this is a logarithmic equation, but we can express this one to its equivalent exponential notation by taking this whole left side of the equation as the exponent of the base e. So e is raised to the exponent of negative t over 22.7 plus the natural log of 45, which is equal to 45 minus 2v. So solving for v, we isolate 2v at the left. So 2v is 45 minus e raised to the exponent of t over 22.7 plus the natural log of 45 here. And using the laws of exponents, that sum of two terms in the exponent can be expressed as e to the power negative t over 22.7 times e to the power of the natural log of 45. And you can check that when you multiply this one, the product must have an exponent which is the sum of these two exponents. But applying the properties of logarithms and exponents, we have e to the power negative t over 22.7 times 45 because e to the power, the natural log of 45 is just equal to 45 since we cancel this one here. So 2v is equal to 45 times 1 minus e to the power of negative t over 22.7 because we factor out the common terms here, common factor here, which is 45. So dividing both sides of the equation by 2, we have 22.5 times 1 minus e to the power of negative t over 22.7. So this is our first answer for the first question in the problem, which is the velocity of the body at any time t. Then, solving for the displacement, we use the concept in calculus that change in the distance with respect to time is our velocity here. So, multiplying both sides of the equation by dt, we have ds is equal to v dt from this equation here. So, taking the integral to both sides of the equation, we have s, which is equal to the integral of v dt. And we know our v, which is this one. So we just substitute it here times 1 minus e to the power negative t over 22.7 dt. So our s here is equal to the integral of 22.5 dt minus the integral of 22.5 times e to the power of negative t over 22.7 dt. And we can factor out the constant outside the integral symbol. So this is 22.5 times the integral of dt minus 22.5 times the integral of e to the power negative t over 22.7, but the differential of this is negative 1 over 22.7 dt here. And maybe you will ask, where did I get this negative 1 over 22.7? I get from somewhere else, but I just neutralize that one by multiplying 22.7 outside the integral symbol, so that this negative 22.7 when multiplied by negative 1 over 22.7, the product is equal to positive 1. So as if I have done nothing to the original integral. But I need this one to integrate this e to the power u, because the du must be here. So this is equal to 22.5 t minus of the minus, which is positive 22.5 times 22.7 times e to the power of negative t over 22.7 plus the constant of integration c sub 2. So factoring the common constant factor here, which is 22.5, we have 22.5 times t plus 22.7 times e to the power of negative t over 22.7 plus the constant of integration c sub 2. But we can solve this c sub 2 by using a boundary condition from the problem that when the time is 0, meaning at the start, our displacement is also 0. So then we can substitute this one to this equation here. So our s is 0, which is equal to 22.5 times 0 plus 22.7 times e to the power of negative 0 over 22.7 plus the constant of integration c sub 2. So this is equal to 22.5 times 22.7 times 1 because e to the power 0 is 1. So our c sub 2, if you move this one to the left, we have negative 22.5 times 22.7. Hence, our formula for displacement, which is S, this one, is equal to 22.5 times T plus 22.7 times e to the power of negative t over 22.7 plus the constant of integration, which is negative 22.5 times 22.7. And again, we can factor out the common factor here, which is 22.5. So 22.5 times t plus 22.7 e to the power negative t over 22.7 minus 22.7 here. And this is our formula for the displacement of the body at any time t. Now let's proceed to our second example here. The landing speed of an airplane is 200 miles per hour when it touches down. It puts on its brakes and reverses its engine. The retardation in its speed is 2 times the square root of its speed. Determine first the time elapsed in seconds from the point of touchdown until the plane comes to a complete stop. And then next is determine the length of runway in feet from the point of touchdown until the plane comes to a complete stop. So to solve this problem is to identify first the given things in the problem. And the given things in the problem is that the velocity is 200 miles per hour and retardation is equal to twice of the square root of the velocity. And we are asked in the problem first to find the time t when the plane will come to its full stop, and then also to find the distance traveled from the point of touchdown when the velocity is 0. So at the point where the plane comes to its complete stop. So to illustrate, allow me to draw an illustration illustrating the situation in the problem. We know that the plane here is approaching the airport here, and then when the plane is touching the ground, so maybe the plane is here, the velocity of the plane at this point of touchdown is given that the velocity of the plane is 200 miles per hour. So this is our start of analysis here. So our distance in the runway traveled at this point is 0. So of course, at the point of touchdown whose speed is 200 miles per hour, the plane will continue to move up to this point here. So this point is the point where the plane comes to its complete stop. So the velocity here is 0. But the time required to come to its complete stop, we don't know yet. And that is our first question. And the second question is, how far did the plane travel from the point of touchdown up to the point of a complete stop. So here, let us write that the retardation of the engine is equal to the deceleration of the motion. So it decelerates because the speed is slowing. So the change in the velocity is negative. In other words, the velocity is decreasing. But we know that the retardation given in the problem is equal to twice of the square root of its speed or velocity. And you can see that this is already a differential equation that can be solved by separation of variables. So here, by separation of variables, and we can do that by multiplying both sides of the equation by dt. So we have dv over 2 square root of v, which is equal to negative dt, by dividing also both sides of the equation by 2 square root of v here. And you notice that the variables are being separated. So we can take the integral of both sides of the equation. So the integral of dv over 2 times the square root of v, which is equal to the integral of dt, but with a negative outside. And you notice that this integrand is the derivative of the square root of v. And surely you can check that if you take the derivative of this, the derivative of this is this one. So this is equal to the negative of t, which is the integral of dt, plus the constant of integration c. But we can solve the constant of integration by using a boundary condition in the problem, that when t is 0, meaning at the point of touchdown, the velocity is 200 miles per hour. But take note that this 200 velocity miles per hour must be converted to a unit that is suitable for our given units in the problem. So let us convert this to feet at this time. So we know that 1 mile is equal to 5,280 feet. But the hour must be also converted into seconds. And we know that 1 hour is composed of 60 minutes, but every minute has 60 seconds. So all in all, there are 3,600 seconds. So the hour here will be cancelled. The miles here will be cancelled. Therefore, our velocity is equal to 880 over 3 feet per second. Or in other words, you can convert it to decimal, that this is equal to 293.33 feet per second. So we can solve for our constant of integration by substituting this v here. So the square root of 880 over 3, which is equal to 0 because the time is 0, plus the constant of integration c. Therefore, our c is equal to 17.13 here. Thus, our equation, which is this one, the square root of v is equal to the negative t plus the constant of integration 17.13. And to answer our first question, what is the time t when the plane comes to its complete stop, meaning the velocity is 0? So substituting this v here, we have the square root of 0, velocity of 0, meaning at complete stop, This is equal to the negative t plus 17.13. So 0, which is equal to negative t plus 17.13. So in other words, the time required is equal to 17.13 seconds. So this is the time required for the plane to come to its complete stop. Now, let's proceed to the second question of the problem. What is the length of the runway in feet from the point of touchdown until it comes to its complete stop? In other words, mathematically, what is the distance traveled by the plane from the point of touchdown when the plane comes to its complete stop, meaning the velocity is 0. So, since we know from this equation that the square root of velocity is equal to the negative t plus 17.13, we can solve for the v. So v is equal to 17.13 minus t to the power of 2 by raising both sides of the equation by 2. And we know that ds dt is equal to the velocity because the change of distance or position with respect to time or per unit time is equal to the velocity of the object. But multiplying both sides of the equation by dt, we have ds, which is equal to v dt. And integrating both sides of the equation, we have the integral of ds, which is equal to the integral of v dt. And substituting our v to this equation, we have s as the integral of ds, which is equal to the integral of v. But our v is this one, so we just copy the square of 17.13 minus t here, dt. And integrating the square of this binomial, we have s, which is equal to the integral of 17.13 minus t to the power of 2 times the negative dt, because the differential of this binomial is negative dt, since the derivative of 17.13 is 0, but the differential of negative t is negative dt. And maybe you ask me, where did I get this negative here? I get this negative from nothing because I multiply here also by negative 1. So that negative 1 times negative here, the answer is positive 1. So as if I have done nothing to the original expression, so that I can integrate this one, because if this is our u, the du must be here. So to integrate, we have the cube of this 17.13 minus t, because we need to add 1 to the exponent, divided by 3, plus the constant of integration c sub 1. However, we can solve for this constant of integration using a boundary condition from the problem, that when at the point of touchdown, so t is 0, there is no distance traveled in the runway because it is just the point of touchdown. So the distance traveled is 0, and then this is equal to the negative 1/3 of the constant times 17.13 minus the time, which is 0, to the power of 3, plus the constant of integration c sub 1. So 0 is equal to negative 1/3 times 5026.574 plus the constant of integration c sub 1. So our constant of integration is equal to the product of this 1 and 1/3, which is 1675.5247. Then, therefore, we say that our formula for S, which is this one, is equal to negative 1/3 times 17.13 minus t to the power of 3 plus 1675.52. And during the time of the full stop, which we have solved it already, that is 17.13. So that's the time when the plane comes to its complete stop. We can find the distance traveled by the plane in the runway. So our S is equal to negative 1/3 times 17.13 minus the time of 17.13 to the power of 3 plus 1675.52. And this is equal to negative 1/3 times 0 cubed plus 1675.52. And anything multiplied by 0 is 0. So therefore, the distance traveled by the plane in the runway is equal to 1675.52 feet, which is the distance traveled by the plane on the runway when it comes to its full stop. So this is our answer for the question number 2 in the problem. And that's it. If you learned something today, please check out my channel for more videos like this and click subscribe. Click the notification bell below so you'll get notified whenever I'll be posting a new video. Don't forget to like this video to show your support. And always remember to math your way up. Thank you.